Very quickly put together a concept that was done by the Advanced Concepts Office at Marshall. They did a fairly extensive study of loft as a probe, and then quickly put things together so that we had things for the STROBE-X proposal. You guys probably know this, but just to remind you, we've got 3 instruments: the X-ray concentrator from 0.2 to 12 keV, the large area detector from 2 to 30 keV, and the wide field monitor from roughly 2 to 50. The effective area is the way that we've defined, at least in the proposal, with 128 X-ray concentrator units and 90 lab modules. We're well above any of the other instruments in effective areas, and we've got the pink line shows you the iron line effective area, so we have quite a lot of effective area there, about 10 meters squared. This may change over the course of the study, but this is what we have in the proposal. So the X-ray concentrator array instrument, in case you're not familiar with this, because I've had questions about this before, it's not a telescope, but it's also not a collimator. So it's a concentrator, so it essentially focuses everything on, with a single bounce on a single pixel. So you can't take out background sources, but it does give you the advantage of much reduced background over something like a collimated instrument. Like NICER, it has very high time resolution of 100 nanoseconds. The optics you see here, the mouse? Yeah. Okay, so these are the NICER optics on the far left, and these are from EXACT. This was a sounding rocket, I believe. The STROBE-X optics will be a scaled-up version from NICER, and they'll have a longer focal length of 3 meters squared and a smaller focal spot, and that increases the throughput above 2.5 keV. These are inexpensive foil optics. It's not the kind of level of effort that's required for something like Chandra optics or something like that, but they give us large areas with low backgrounds. The detectors have very good energy resolution, 85 to 175 EV. In the proposed design, we've got 3.4 meters squared of effective area at 1.5 keV. So these are using the NICER detectors as well, so the technology is definitely being space proven as we speak. NICER's working beautifully. So this instrument is very exciting because it gives us kind of a super NICER, you could say. The large area detector is taken from the loft concept. It is silicon drift detectors and lightweight microcapillary plate collimators. The lightweight collimators allow the large effective areas compared to traditional collimators like were used on our XTE. This has got 10 microsecond time resolution and good CCD quality energy resolution. Very large effective area, 7.6 meters squared at 10 keV. The energy resolution shown here is what was true for loft, and I'll talk about that a bit more later. The wide field monitor, the third instrument, while much smaller than the other two, is a very important instrument for our science. It's viewing a third of the sky at any one time. It covers the 2 to 50 keV energy range. So it's a pathfinder for the large instruments. It will trigger on outbursts and that sort of thing that we will want to follow up. And at the same time, viewing a third of the sky, it will do its own science with 10 microsecond time resolution and 300 EV energy resolution. It's got a positional accuracy of 1 arc minute. So there's a lot we can do with this, and so it's going to be something I guess I didn't mention. The 2 large area instruments are co-pointed, and the central cameras of the wide field monitor are co-pointed. And then the rest of the field of view is the third of the sky around where the instrument is pointing. So we, as a pathfinder to the instrument design lab study. We did a bit of looking into launch vehicle capabilities. We talked to NASA Launch Services. Well, first we talked to Gabe Capardi about Falcon Heavies, and he told us that they would be $500 million for purposes of this study, which basically means they're not usable. At the time we actually go, it may be possible, but we can't include that in this study. So we have to stick with a regular Falcon 9 launching from Kennedy Space Center, Cape Canaveral. And the study that Launch Services did for us was to look at how much mass could be launched to a given orbit, and comparing the drone ship recovery and an expendable first stage. On the Launch Services website, currently the only choices for Falcon 9s are the drone recovery and the landing there at KSC. The landing at KSC is useless for us. We can't get enough mass up for anything. The drone ship recovery, so on this plot here, the blue line is the drone ship first stage recovery, and the green line is the current STROBE-X mass, and that's based on the very quick study that ACO did. We're slightly above the 15-degree point because the current STROBE-X mass is 5,820 kilograms. Now this is an engineering study mass, so it does include all of these margins and contingencies and all of that. But this was based on an extremely quick study and a wild guess on what the structure was for the X-ray concentrator array. So this will be refined in this study. With the expendable first stage, we're in a lot better shape. We can certainly get below 15 degrees, even with quite a bit of mass margin. We might be able to get closer to 10 degrees if we can lose a little mass. And the reason this all matters is the lab detectors. There's an issue with leakage current that is increased by radiation damage in SAA, and this happens pretty quickly within the first year of the mission. So the higher the orbital inclination, the higher the radiation damage, and the worse the spectral resolution, the energy resolution. So to mitigate this, Loft selected a very low inclination orbit of less than 2.5 degrees. This is something we can't do. So we can probably get to 10 to 15 degrees. So that's what we're going to have to shoot for. The other effect that can mitigate this is operating temperature. I'll plot on the next slide. Hopefully shows up. Yeah. So this is from the M3 study. The two curves, which you can vaguely see the colors on, are from two different point designs for the M3 versus Loft. The line across the middle here was minus 10 degrees, which was the operating temperature for the 2.5 degree orbit, and you can see that the field of regard was pretty wide. This is the angle with respect to the sun. So essentially it's looking in anti-sun directions. And then they had an extended field of regard where you could still operate with somewhat degraded resolution. For a 20 degree orbit, a 20 degree inclination, you need a temperature of minus 30 to keep the energy resolution below 300 keV. Now, I keep saying keV, sorry, wrong field. EV. So that's way down here on the curve, which is problematic. We can't do that. So there's a number of things we'll have to consider in the study and take a closer look at this. Is there some sort of cooling that we could consider? And Marco has told us about some design improvements to the detectors that might help a little bit. This is something we need to look at in more detail during the study and figure out how to best address this. And for this, it's important that we know from you guys what is the energy resolution you really need to be able to do your science with the lab detectors. So the trades that we've thought about that we'll do in the study are the effective area of the two large area instruments. where do we really need the effective area to do the best science? What's the best ratio between the two instruments? As I talked about a bit, there the orbital inclination versus the launch mass. That affects energy resolution and effective area. The field of regard, that's the amount of the sky that's visible, accessible to the lab. That's part of that trade as well. The other thing that we'll be addressing, especially in the instrument design lab run, is the design of the optical bench that holds the X-ray concentrator array and that holds the support structure for the development of the deployment of the lab panels. That's important to the mass of the spacecraft to figure out what that kind of drives our mass quite a lot. We also want to optimize the detail of the X-ray concentrator array and the mirrors. Something that Paul mentioned is that we need to be able to fairly rapidly repoint. Something we need to figure out in the study is exactly how rapidly and how often can we repoint. I've been asked during talks, can we repoint during Earth occultations? This drives things like reaction wheels and other, I can't think of the word, what is it, something momentum gyros. CMGs, yeah, I can't think what C stands for. Control, thank you. Control momentum gyros. What sort of trays we had there in pointing capability. So I gave a talk on STROBE-X at AAS last January, and one of the things that came up there, David Burrows suggested that we have an onboard repoint capability so that it could automatically repoint like Fermi does. We can make that programmable so it doesn't happen too often for our pointing capabilities, but it's definitely something we want to design in there somehow. And the last thing, of course, we'll have to study is the telemetry. I mean, we're thinking event-by-event data for all instruments, but again, we need to know from you guys what do you absolutely need, so that if we need to limit telemetry, where can we do that? And this is my last slide. Basically just asking what design parameters does your science drive? What do you need the most, and what can you not do your science without? The better we understand this, the better we can understand we can design a very capable mission to do the best science. And of course we'll have to make some trades, but if we understand the trades well, then we can consider them in the studies. And that's all I had.